Hi there, for a change a reasonably short repair video. I bought this light meter as not working from eBay. The seller said one of the battery terminals had corroded away. Battery corrosion is sometimes non-repairable if it destroys tracks on a multi-layer PCB, but at £10 or about $12 US including shipping, it was a risk that I was willing to take. You can still buy this meter new from RS Components at an eye-watering price of £169 or about $208 US including tax, and lots more if you want it calibrated. So if I can get my eBay find back into working order, this would be a real bargain. From the outside it looks in excellent condition, and it even has an RS-232 output. So let's have a look at the problem battery terminal. The battery door is certainly very hard to open, which could be a bad sign. But no, it all looks surprisingly clean. Oh, and there's the problem. The contact for the plus terminal of the battery clip has vanished. I don't think this was corrosion, more a mechanical problem. Maybe the terminal was badly riveted. If this is the only problem, that's an easy fix because I have plenty of spare battery clips. Let's open it up because I want to see the inside, and anyway I need access to replace the battery clip. The housing is held with 4 screws that are not self-tappers. Just from that you can see this is not a low budget device, right? Okay, finally I have it open. The design follows the usual way in that the battery cable is run through a hole in the PCB as a strain relief and then soldered in. This means of course I need to get the PCB out to get to the underside for soldering. It does not look as if the PCB is held in with more screws, and indeed with a small screwdriver as a lever it is possible to lift it out. There's hardly anything on the underside. The first job is to desolder the wires leading to the old battery clip. I do have a desoldering gun, but setting it up and cleaning it afterwards is more trouble than this job is worth, so I decided to use solder wick instead. That should have done it. Now it's just getting the old wires out. They are of course still attached with whatever is left of the solder. In hindsight I should have spent a little bit more time in preventing the PCB from sliding around so much, but in the end it worked and I got both wires out without damaging anything and leaving nice clean holes for the new wires. I put the wires of the new clip in, leading them first through the strain relief hole of course. Now all that's left is to solder them in. It's not my best soldering work by a long shot. I blame the camera which is in the way and preventing me from better positioning the board to make soldering easier. But anyway, in the end it's done. All that's needed is to stuff the new battery clip back into the compartment where the battery will sit and put the PCB back the right way up for the moment of truth. Adding a new battery, and now where's the power button? Okay, the display comes to life. That's a good sign. It just shows dashes though. It's probably because the sensor isn't plugged in. Let's do that now. And opening the protection cap. Well, that's kind of underwhelming. Still showing just dashes like before. Randomly trying some buttons doesn't do much. Let's try the switch. And now we have a reading in foot candles apparently. And the number goes lower when I cover the sensor, which makes sense. Changing the display to lux and it's a much bigger number now. The switch has to be in the most left position to show any readings. Oh yes, of course, it's the range switch, and with 1500 lux or so, we need to be in the lowest 2000 lux range. Before closing it, a quick look at the innards. It's a double-sided board and it doesn't look too complex. The visible chips are 4013, which contains 2 D flip-flops, a low offset op-amp in form of the OP07, and the AME7106A, which is an analog to digital converter directly driving a 3.5-digit LCD display. The LCD is glued in with something like hot glue, which is why I left it as it is, but there must be some microcontroller of sorts under it to run the show and provide the RS-232 output. The underside of the board is pretty empty apart from the 3 trim pots arranged in a way you can do adjustments through the open battery compartment and a socketed 1K EEPROM. The round wheel on the top reminds me of the volume control in old school transistor radios, but in this case it allows adjusting the LCD contrast. So much about the light meter. What about the sensor? It says calibration void if seal is broken, but who cares? And I was always curious what is in these things anyway. So let's open the 3 screws and find out. Not a lot apparently, well certainly less than I expected. It's some sort of a 2-pin optical sensor under some greenish filter window. The question is whether this produces light dependent voltage or if it's a light dependent resistor. I then discovered this section in the meter's datasheet. It's a photodiode, and it and the color filter are specially selected to meet some standard. It is indeed a photodiode. With the sensor unplugged from the light meter, it produces about 0.2 volts at the moment, which gets lower when I use my finger to cast a shadow over it. Last thing to examine is the white diffuser window of the sensor unit. It is actually more opaque than I expected. It looks as if not much light is getting through, but obviously it's still plenty when shining a fairly bright LED torchlight through it. With the meter back together, a quick demonstration what it can do. The first job is to cover the sensor with the provided cap and zero the meter. Then with the cap removed, the meter shows the illuminance on my desk either in lux or in foot candles, whatever that is. You can switch it to a percent mode where it takes the current measured value as 100% and shows the variance from that in percent. Turning percent off and we are back to normal with the reading in lux. When pressing record, the meter starts tracking the maximum and minimum values measured, and using the core button cycles between the display of maximum, minimum and the calculated average. Hold does the usual thing of freezing the displayed value. The L on the bottom row of the display indicates that the meter is set to measure light from tungsten lamps, which is the default. You can switch it to other light sources. F stands for fluorescent lamps, S stands for daylight, C for mercury lamps, and back to tungsten. The range selection is kind of cute and unusual. First, going from the 2000 lux to 20,000 doesn't show anything. Despite having over 500 lux at the moment, the display shows no number, just the lowest bar of the 7 segments to indicate an underflow. Lifting the sensor closing to the light source, and now we see reading and have to mentally add 1 0 to the right, which is indicated at the bottom. The 50,000 lux range adds 2 zeros. Going back to 2000 lux range, now the display is showing an overflow using the upper segments. Just for reference, here are some typical illuminance values from Wikipedia. It is clear that with an upper limit of 50,000 lux, the meter can overflow even with the highest range, but I suppose direct sunlight is not a case where a light meter is really needed. I also noticed that in direct sunlight I saw values over 60,000, so maybe its accuracy is no longer the claimed ±4% plus 2 digits when you exceed 50,000. The other table is my guess at what different light sources mean. The only value I know for sure is the tungsten one, because this color temperature is stated in the datasheet of the meter because it has been calibrated using tungsten light of that temperature. The other values are just guesses because nothing is stated in the meter datasheet, and there are wide ranges of color temperatures for each type of light on the internet. And the mysterious foot candle unit? 1 lux is defined as 1 lumen per square meter, and a foot candle is simply using a square foot instead of square meter. But what are lux anyway? Long-time viewers may remember this from my series of building a station measuring all kinds of environmental data, including illumination. Illuminance, measured in lux, is how bright something appears, taking into account the way the human eye works. It's the number of lumens hitting an area. Lumens in turn are the quantity of visible light emitted from a source per unit time. If you had a light source radiating a known amount of lumens, say 1000 in all directions, the lux number drops the further away you get because the area increases. Because we are talking area here, the lux number drops by the square of the distance. 0.4 meters away, the area of the sphere is 2 square meters, and so we got 500 lux illuminance. Doubling the distance to 0.8 meters, and the sphere now has an area of 4 square meters, which means only 125 lux is left. Think of it as the light has to spread thinner to cover more area. Here I have a set of LED light bulbs that claim to emit 470 lumens. Of note, these light bulbs are emitting light only in the angle of 210 degrees. And here a claim of the color temperature being 2700 Kelvin, which I think is close enough to use the tungsten setting of 2858. Plugging this into the formula at 0.4 meter distance, the 470 lumens need to illuminate only an area of 1.16 square meters instead of 2 if the bulb was shining into all directions. So we should end up measuring around 402 lux at a distance of 0.4 meters. This is my rather crude setup. I show it now because it will be harder to see when all the other lights are off, except the test bulb, which is mounted as freestanding as I can. The measured value depends on small variations of the angle I hold the sensor relative to the bulb and small variations of distance, but all in all, I'm quite pleased with the result. Last not least, the serial port. Accessing is easy. Any 3.5mm tip sleeve or tip ring sleeve jack will do. And there's a fairly beefy, in terms of amplitude, RS-232 signal coming out. It is meant to be used with this data acquisition software called SW-U801-Win, which costs in the order of $50. ISO 9001 and whatnot, but can't spell Excel or Access. Anyway, I found the operation manual on the web, and the only useful information I got out of it is that the serial speed is apparently either 2400 or 9600 bits per second. Important information that is sadly absent from the meters documentation provided by RS. Here's all that RS tells you about the protocol, and I wrote a little tool trying to read the serial data stream. 9600 bits per second seems to be correct, and while I can see that the bytes on the right in the window below change when I shade the sensor, the decoding doesn't make much sense. There's a lot of hex 07 where I would expect 00, for example. I decided to leave it alone for now and keep the video short, but I may investigate it someday. So don't forget to subscribe if you have not already, and maybe consider becoming a Patreon, link in the description. As a Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.